Lake textbook, and we've gotten through every chapter in the textbook. We're going to finish off with Chapter 18, which talks about searching and sorting algorithms. And so a lot of this is review from 150, 141. Oddly enough, probably encountered this in 241 as well. So we'll finish this up and take a look at some ways to search through data structures. Basically, searching is pretty important in computer science, and using search algorithms, you can determine whether a particular item is in a list, if its data is organized, and find location in the list where the new item can be inserted. If you're looking to insert something and keep the list in order, find the location of an item to be deleted from a list. And data can be organized with the help of an array or a linked list or any other type of data structure. But a lot of times we have to search through those data structures in order to perform the actions that we want to accomplish. So an important term is the key of the item. This is a special member that uniquely identifies the item in the data set. And what we do when we search is we conduct a key comparison. We compare the key of the search item with the key of the item in the list. So, hey, have we found this? And we can count the number of key comparisons in order to see how well our search performs. So let's go back and look at our first search that we ever learned, which was a sequential search. And sequential search is great for unordered lists. It's also known as linear search, and it works the same for both arrays and linked lists in terms of its overall structure. Start at the first element, check and see if that's it, and examine each element until a match is found. Most implementations use an iterative approach, but it can also be implemented with recursion. If you're using something like LISP or Haskell, and it makes it kind of fun. I'll make sure to show you how that works. So here's the C++ version that and you're probably comfortable with. So you're going to return an integer, which is where you found the particular item. You are searching through an array of integers. In this case, the size of the array is n, and x is the item that you're looking for. And you basically do a loop that's the size of the array. If the array at that index is equal to what you're looking for, you return the index. Otherwise, you return -1, which would indicate that you didn't find that in the data structure that you were looking through. The fun Lisp version, and now you're going to get the lion joke. How do you find the lion in the zoo? You look in the first cage. If the lion's there, you found it. Otherwise, look in the rest of the zoo. So basically what this Lisp version does is it says if you have found if the item in the first element of the list is what you're looking for, then you return that item's position. Otherwise, you search the decremented list, CDR. That means the list with the first item removed for the item and move forward one position. So that's the recursive version, and it's kind of a fun one to implement. So there's a couple different ways to implement sequential search. So the statements in the traditional form, the iterative version, before and after the loop only get executed once, and so that requires pretty small amounts of computer time. What we're more concerned with is the for loop, which is repeated n times, and execution of other statements in the loop is directly related to the outcome of the key comparison. So we're looking at the key comparisons specifically. So how much work is involved? Well, if we have a list of linked n and we're looking for an item that's not in the list, then in the worst case, we're going to make n comparisons. If the search item is in the list, the best case scenario is it's in the first. We find the lion in the first cage in the zoo, and we're done. And again, probably the worst is it's the last element in the list, in which case there's n comparisons. The average number of comparisons is n plus 1 divided by 2. A lot of times we're interested in the worst case rather than the average case, but here we can actually find the average case. So the other search technique is binary search, and binary search has to work with sorted lists. If the list isn't sorted, you can't really do binary search, and this uses a divide and conquer technique. You compare the search item to the middle element. If it's Less than the middle element, search in the first half. If it's greater than, search in the second half. And this works for things like textbooks or dictionaries, if you're looking in lexicographical order in the dictionary, or you're looking in numerical order in a book for a particular page. Binary search is fast. Every iteration cuts the size of what you're searching through in half. So if you have 1,024 pages in a book and you're looking for a particular page using binary search, then you would have 2 raised to the 10th items and most 11 iterations needed to find X if X was particularly difficult to find. Every iteration will make 2 key comparisons, and so in this case you have at most 22 key comparisons, and the maximum is 2 times log 2n plus 2, so this is O of log n. And sequential search in contrast is going to require 512 key comparisons to find if X is an L. So some notes on big O notation, and again, you should be familiar with big O notation from CS 141 and CS 241. If you're not, we'll cover this in a little bit of detail. I'll leave the gory details to 141 since that's where we treat it. After you design an algorithm, you need to analyze it. How well does this algorithm do? Again, we look at algorithms from various viewpoints. Is this algorithm understandable? Does it return the correct answer? Or, how good are the answers? If we're doing something that's a heuristic algorithm, we might evaluate it based on its correctness. We want to look at its efficiency and its elegance. A lot of times an elegant algorithm is something really cool to implement. And so there's different ways to design algorithms for particular tasks. And certain algorithms take very little computer time, others take a lot. So efficiency is a prime consideration. So big O notation says let f be a function of n, and the study of the function as n becomes larger and larger without bounds. So how does this function grow? And the formal definition is let f and g be real-valued non-negative functions. F of n is big O of g of n, wherein f of n is equal to capital O g of n. If there are constants c and n0 such that f of n is less than or equal to c times g of n, for all n is greater than or equal to n0. And basically, here your constants c and n0 are known as witnesses. So, can I think of a function g of n such that c times g of n is bigger than f of n for every value of n greater than some value? And most of the time I can. And so it's pretty easy to say sequential search, which is O of n. You could also say sequential search is O of n squared. So a lot of times we're interested in getting a more precise bound, and commonly that's what we mean when we talk about big O. But you can also abuse the definition just a little bit. So some growth rates for common values of big O. And again, this is how many comparisons you might do. If it's log n and the size is 32, you're going to do 5. If it's 2 to the n, you're going to do a hideous number of comparisons. That's 4 billion. That's 4.2 billion if it's 32 and you have a 2 to the n algorithm. 4.2 billion versus 5. It's quite a huge difference. So the way that you construct an algorithm is tremendously important in terms of efficiency. And if you were executing 1 billion operations per second and you had a problem of, say, size 100, if it was n, then that would be something like sequential search. It would take 0.1 microseconds. If it was 2 to the n, it'd take 4 times 10 to the 13th years. And if it was size 1,000, you can't even get it done with the time that's remaining in the universe, or it's too large to really consider. So we can also analyze the growth rate using graphical depictions of the functions, and you can see 2 of n exponential growth. as we found out with COVID-19, is quite a scary thing. It takes off and it grows fast, whereas login, it has that nice shape, and we can extend the problem out and apply it to bigger and bigger data sets. So a nice summary, if it's constant and doesn't depend on n, that's perfect. That's something like making a calculation. Log base 2 of n is a function that grows slowly, such as binary search. In the growth rate is linear, like sequential search. In log m, which we're going to see a lot in sorting, it's faster than a linear algorithm, but it's still pretty good. And n squared, it increases rapidly with the size of the problem. It's quadrupled when the problem size is doubled. And the one we really, really want to avoid is O of 2 to the n. Basically the growth rate is exponential and squared when the problem size is doubled. So that's what we definitely want to avoid. So in summary, in looking at our two types of searches, sequential search for a successful search is O of n, unsuccessful search is O of n. Binary search, successful search is O of log n, and a unsuccessful search is O of log n. So binary search is the winner, but it does assume that you are working with a sorted list. And it's important to know the speed limit. This is a theorem that goes on for a long time, but basically it says any search that relies upon key comparisons can't go faster than log 2n. So basically it says, hey, you can't do better than binary search if you're relying on key comparisons. So next time we'll take a look at sorting.